Look, I've got a problem. You see, for the past few months, I've been working on a 3D printed gas engine. However, there's still one problem that I can't avoid. Just like this water bottle, it's made from plastic. And also like this water bottle, it can't take the heat. But after some long thought, I realized what I must do. And I know just who can help. So today, I'm going to be rebuilding this engine using metal 3D printing. Unlike a regular 3D printer that passes melted plastic through a tight nozzle, a metal 3D printer works by firing a laser into a big vat of stainless steel dust, fusing the dust into the shape of the part layer by layer. Now, PCBWay has other solutions like CNC work or sheet metal work, but given that this is the 3D printed gas engine project after all, we both agreed it only made sense to go with metal 3D printing. And on that note, I gathered all the parts I needed, then sent them over to PCBWay. And a little after a week, they've arrived. Now, actually being able to hold a metal 3D printed part in my hand is kind of surreal. I think the best way to describe its texture is like that of a cold, heavy stone. In any case, before I can use this part, it's gonna need some work. So I'm gonna start with tapping the holes so I can thread in the machine screws. Now, tapping the holes is a pretty straightforward process, as the whole head is made from stainless steel, which is not only tough, but fairly easy to work on. And because the head is made from metal after all, it only makes sense to switch to using a spark plug, so I'm gonna tap the hole for that too. However, I ran into a problem. That is way too tight. As it turns out, when I was designing the head, I made the hole for the spark plug a little too small. So not only is it cutting threads, but I'm also slightly resizing the hole. And I know this looks pretty bad, and that's because it is. What makes this whole situation even worse is PCBWay will tap specified holes for you if you provide them with the drawings, but I thought it'd be more fun to do it myself. However, with plenty of oil, careful persuasion, and enough time, I was able to get the tap through the hole far enough that now I can thread the spark plug all the way in. And if you're wondering why I didn't think to resize the hole with a Dremel before doing all that, I don't know. In any case, the surface that's going to be sealing against the head gasket is rather rough, so I not only smoothed it down in my belt sander, but I also did the surface that seals against the intake manifold as well. And now it's looking pretty good. However, there's just one last thing. The valves. Before I can make any use of these, I'll need to first do something about this rough surface. Of course, you can't just grind metal on metal. You'll need to use a lapping compound. Think of it like toothpaste, but for metal. Now I'm first starting the grind with a power drill, so that way I can remove a lot of material. And then at the end, I'm doing the polishing by hand, so I can create a nice even seal. And I'm happy to report after my first round of lapping, it was working really well. However, there was still some pitting on the valve and the head, but nothing another 5 minutes or so of hand polishing can't fix. And now we're looking good. The clever thing about this lapping compound is that the grit size of the abrasive particles are very rough, so it removes a lot of material quickly. But the more you use it, the grit gets finer and finer, which polishes the surface. After marking which valve belongs where so I don't get them mixed up, all that's left to do is tap the threads that will be used to connect the valves to the valve springs. Then finally, the head will be complete. Okay, never mind, I broke the stem off. And I actually thought this might have happened, which is why I requested that they send me a few extras just in case. But since I already went through the trouble of lapping the valves, I think what I can do is replace the stem with a screw I cut off earlier. And I did this by first cutting off the threaded portion of the stem. Then I welded the new screw to it. It looks kind of ugly, but it seems to make a great replacement. And with that out of the way, the next and last part I want to have a look at is going to be the piston. It feels very nice and well made, just like the other parts PCBWay provided me. But there's just one problem. Let me show you on my computer. It's very heavy. Of course I knew this. It's pretty obvious that making a piston from solid steel will be significantly heavier than one made from a semi-hollow plastic. And this is a problem because if we take a look inside the old engine, not only are the crankshaft counterweights far too light, but I am positive this new piston will easily snap this connecting rod in half. So in preparation for the new piston, I'm going to make a new rotating assembly, starting from this drawing. I made the scale of the drawing 1:1, so all I have to do is cut them out, and then stick them on this piece of flat bar. Now instead of welding the crankshaft together into one piece, I left them separate with the idea that they will fit together during assembly, kind of in the same way that a motorcycle crankshaft works. Now for the connecting rod, my first idea was to use a section of this steel pipe to form a journal bearing. Since the pipe is oversized, I cut out a small section of it and reduced the size by crimping it in a vise, which worked really well. It had virtually no play, but also spun freely too. I repeated the process again, then welded everything to a steel rod. And this seemed to work at first, as it spun freely under its own weight, but I would come to discover that under load, my makeshift bearing was catching with the shaft and binding with it. So the only logical course of action was to use an actual bearing to fix the problem. However, when I compared the mass of the piston and connecting rod against the crankshaft, I could already tell that it was not going to be heavy enough. So as a quick fix, my plan is to drill a hole into the outside of the counterweight that's just large enough for me to seat a steel ball into it. And here is the final result. Not only does everything rotate very smoothly, but I'm confident that the engine will be fairly well balanced. And to fit the new crankshaft, I made a new crankcase. It's not only bigger and stronger, but I also tapped out the oil filler neck on the back side, so I could fit a proper oil cap. But as I was putting it together, I realized there isn't enough clearance above the counterweight, causing it to hit the top of the case. So instead of making the crankcase bigger, I think what I'll do is make the counterweights a little bit smaller. Even though I removed some material, it should still be heavy enough to keep the engine fairly well balanced. And to wrap this up, the last part I need is the cylinder, which I'm going to make on my 3D printer. Just in case you're wondering why I didn't go with an air cooling cylinder made from metal to go with all the other parts I had made, well, metal 3D printing is really expensive. The engine head alone was $320, the same part I almost buried a tap into. Because metal wasn't an option, I came up with this. It's actually pretty similar to the one I made in the last video, which if you recall, immediately leaked everywhere and was a huge pain in the ass. But this one is different. It's made from two parts that are glued together to seal the water inside the jacket, but it's also designed to support all the force from the engine head, to prevent the top of the cylinder from caving in when I tighten the bolts. I also made sure to change a few print settings that should help with waterproofing. But just to be sure, I grabbed the same water pump as before, then went inside to grab a glass of water. And if I did this right, when I turned the pump on, the water should flow from the glass to the jacket, then back to the glass. And it kind of works, but not very well. I thought this was because the cooling jacket was way below the water level, making it harder to pump, so I tried moving the cylinder up to the same level, which still didn't work. Out of curiosity, I set the glass up high and siphoned the water out. And the moment I connected the tube to the cooling jacket, the water ran all the way through. What this means is there isn't anything wrong with my design, but rather I think this water pump just isn't powerful enough to push the water through the whole system like I need it to. So I bought one of these. It's a water pump designed for a fish tank. And I can already tell from this little test I conducted, it has the ability to flow much more water than the other pump. Also, this feels very wrong, placing this cheap piece of plastic into a jar of water then plugging it in. But hey, it works really well, and when I hook it up to the cooling jacket, the water is able to actually flow through the whole system at a constant rate. Granted, it does seem to leak a little bit of water, especially around where the tubes enter the jacket, but overall, it seems to hold water way better than before. Alright, so now that's out of the way, I want to get back to the piston. Just before I can put the piston into the engine, the first thing I want to do is remove the sharp edges on the piston skirt, so that way they don't chew up the brass cylinder walls. And I also filed out this hole so that the wrist pin can fit in snugly. However, because I don't want the wrist pin walking out of the piston while the engine is running, I took these two really stiff springs and pressed them in sideways to lock it in place. And after putting it together this far, I'm very pleased to find that everything seems to be moving freely. But let's not get too excited just yet, because until I know for sure that this engine has decent compression, this will not be going anywhere. Holy crap. Not only does it have good compression, but the lapped metal valves actually seem to do a much better job at sealing than the valves from the last video. And after putting it all together, all that it needs is a fill up with oil and we should be good to go. And you'll notice that I'm no longer using alcohol as a fuel source, and that's because I decided to get rid of it. Then switch to using gasoline. Now that the piston and engine head are both made from metal, the gasoline should be no problem. And for this first test, I actually had a second camera set up off to the left, but for some reason the memory card got corrupted. But that's okay, because you're not really missing much. The engine would run in a very short burst and then stall out. And after doing this a few times, I started to suspect that there's not only some water leaking in the crankcase, but also some gasoline as well. Sounds pretty wet. But I think if I make a few changes to the ignition timing, it'll come to life. Never mind, I think I broke it.
Yeah, that's not supposed to happen.
But just to be sure, it's still worth having a look on the inside just to see what went wrong.
Oh, that's not supposed to look like that.
No, it's not, as the welds that were supposed to hold the bearing to the connecting rod broke clean off. But hey, everything else looks just fine. And I'm willing to bet after giving these really greasy parts a much needed clean, it's just a matter of fixing the connecting rod before we're back in business. Anyways, I put the engine together once again and hey, isn't that the same cylinder you used in the last video? Well, you see, on its own terms, the water cooling jacket seemed to work just fine. But once it was installed on the engine and placed under stress, it immediately leaked everywhere. I really hate to disappoint, but I don't think there's much of a way to make a watertight cooling jacket on a regular FDM printer like mine. In any case, I tried to fire it up once more, but not long after, I noticed the crankshaft started to become really loose. But instead of stopping, I kept trying to get it going. I don't really know what I was expecting, but it certainly wasn't this. One of the 50 caliber steel balls on the edge of the flywheel dislodged itself and flew right off. I never actually saw where it went, but watching the video back, for only a single frame, you can see it flew right past my head. So I think I'll take this as a sign to submit. Because the hole in the counterweight is pretty thin, the stresses on the crankshaft started to widen it, so now the crankshaft bows like this. But since I'm now satisfied with the connecting rod I already have, I really shouldn't need to take it off again. So what I can do is cut off the counterweights. Then slip them over the same shaft so that when I weld everything together, they will be perfectly aligned. As for the flywheel, however, not only did this thing try to kill me, but it's also got this huge chunk taken out of it as a consequence of my last video. And the other issue I have with this flywheel is that it just barely meets the amount of threshold inertia required to get this engine to even run. So, it's gotta go. Naturally, in the middle of the night, I went sleuthing in my backyard to try and find an alternative. Like this tire, it's round and should have more than enough inertia. Or how about this go-kart I cut in half, which clamped to its drive shaft is this big toothed pulley. But remembering I have this old lawnmower engine, I think I found my solution. Because the drive shaft is an inch thick and I don't want to cut through all that, the only alternative is to remove all the seized bolts around the perimeter of the pulley so you can separate the two halves. And this was going very well.
Finally.
This pulley is not only significantly heavier, but it's actually not that much larger in diameter than what I was using before, so making the conversion should be pretty easy. And speaking of conversion, I need to find a way to fit the pulley on the engine's output shaft. And as luck would have it, the drive shaft I literally just cut off is not only the perfect diameter, but it also has a matching key cut into it. The only hard part is going to be boring a perfectly centered hole without the use of a lathe. But if I flatten the face of the shaft on a disc sander, I can use this convenient little tool called the center square to draw a bunch of lines that should cross in the middle. And after cutting the end off and boring it out, I now have this little adapter that mates the flywheel to the engine. And to lock everything together, I made this key from a thin piece of steel that slots in between the starting hub, which was easily fitted to the flywheel by drilling and tapping holes into the aluminum pulley. Now, since there's nothing physically in the way of letting the flywheel just walk off, the key should create enough friction between the two, keeping it locked in place. Or at least, God, I hope so.
That could hurt.
In any case, it's evident that this new flywheel is much better. Not only has it reduced my risk of instant death from 70% to just 20%, but it's also fairly well balanced too, which is great, because now I can test the engine once again. And I was not expecting that.
Dude!
Since the engine runs so much better now, I thought it was worth seeing what it looked like in slow motion using my phone. Alright, so now for the real test. I connected it back up with gasoline in hopes that I can mess around with the throttle while the engine runs.
3, 2, 1.
And it kind of works. But really, all that I've done is just flood the engine with a lot of gasoline. I will figure something out for the future, but for now, let's just enjoy it for what it is. Thanks to the small oil leak, the flywheel was able to slip off, crashing straight into my bench on the right side. So for a quick fix, I just wrapped some chicken wire around the flywheel to prevent it from ever getting off again. I noticed the engine runs for much longer, but it still slowly stalls out. And I think the reason why this is happening is because it's sucking in the fuel at a slightly faster rate than what the torch is able to provide. But in any case, it doesn't seem to have any trouble firing right back up. I was shocked at how tough this thing was. And for the very first time, I think this engine might actually be able to outlast my ability to destroy it. But eventually, it developed a slight knock. And also started to blow some smoke. I also noticed it wasn't as eager to start, but it still did. That is, until this happened.
Okay. No, I'm done. I'm done.
The engine backfired through the intake, blowing the manifold right off. Remarkably though, it still had really good compression, and if the intake didn't blow off, I'm sure the engine would have ran for a little bit longer before something else broke.
Unreal.
Now before I take a look on the inside of the engine, I've got to drain all the oil. Interestingly, after all of that testing, the oil is significantly darker than its initial golden color. Now the head and head gasket both look fine, beyond just being a little wet, and same with the rotating assembly, everything feels the way that it should. But the most interesting part is that even though there was no cooling system, the O-ring never got hot enough to melt, and nor did the plastic cylinder either. Before I wrap things up, I really want to thank PCBWay once again for making this all possible. PCBWay offers everything you could ever need from 3D printing, CNC machining, or indicative of their name, PCB fabrication. So if there's ever anything you need done, definitely check them out. As for the engine, I can't think of very many things left to do to improve it. I think that I'm finally satisfied. But don't worry, because this is definitely not the last time you'll see me make an engine on this channel. Thank you so much for watching this video, and if you enjoyed that, check out some of my other projects. Anyways, that's all for today. Peace, guys.